Let's continue studying normal forms of hyperbolic transformation, and we will so far keep studying the transformations with two fixed points. So if you have a hyperbolic transformation, W equals Tz with exactly two fixed points, then the so-called normal form is a convenient form of viewing the hyperbolic transformation, and it also allows us to see how the lines that are important for us move along the complex plane. So how do we do it? I will remind you briefly. We consider, first of all, we will make a transformation S that sends, I will write it this way, S Z sends P to 0 and Q to infinity is done by means of transformation S. Then we are arriving, we are here is Z plane, yes? This is Z plane. From Z plane we take P to 0 and Q to infinity. Then there will be a transformation R that keeps these fixed points. But this transformation is a transformation in this, we will call Z plane, which is being transformed into W plane. It is the same plane, of course, but I just want to say that W is RZ. Yeah? Here, SZ is Z. Right? And these 2 points are mapped again to the Z plane, but we will call this variable W, what we obtain as a result of transformation T. So this will be transformation S minus 1 that sends S minus 1. It's the inverse of the original transformation S that sends 0 back to point P and infinity back to point Q. This will be the W plane. W plane, where W is Tz, where T is our transformation. That's the whole thing, how it happens. Why do we need to do it this way? Because it is a convenient form, which we call normal form. I insist that these notations are better than notations which are chosen in your text, which are slightly confusing. So let's see what happens here. We perform transformation S Z equals Z minus P over Z minus Q, and this I will denote Z. Then W will be lambda Z. This way it preserves point 0 and infinity as fixed points. And then S minus 1 W will be W small. Thus the whole transformation W equals Tz can be written as S minus 1 applied to W, which is applied to R, which is applied to SZ. Yes? And the whole this transformation, so the composition of 3 transformation applied to Z. Technically, it is convenient to write it this way. How to move point P to infinity, P to 0, Q to infinity. You can write it this way. You can write Z minus P over Z minus Q. And then this way we will obtain Z. And Z can be must be multiplied by lambda. That's how we do it. So I will write it this way. W, this is our W, yes? W minus P over W minus Q. This is transformation S minus 1. This is transformation S that takes P to 0 from the W plane, right? We take P to 0, Q to infinity. So by S minus 1, we move it backwards, equals lambda Z minus P over Z minus Q. Let's make this formula number 1, and this is called the normal form of a Möbius transformation. And the whole question is about lambda. What happens, now I have to raise something and to draw some lines that are important for our consideration. Steiner circles. These lines are called Steiner circles of the first kind and second kind. And these circles are of course circles for lines, because there is no difference between them in Möbius geometry. So there is point P and there is point Q, and there may be a few circles joining these points, a few, there are infinitely many of them, yes? That pass through these points, pass through these points. And so on. Yes, we may have more. This circle. And so on. Right? And these are Steiner circles of the first kind. Steiner of the first kind. And we can also consider circles orthogonal to these circles. And we will do it in a second. But so far, I want to perform a transformation. I perform transformation S that moves P to 0, Q to infinity. So it will be lines, there will be lines because one of the points is infinity, then these lines are lines passing through the origin because P is mapped into 0. And of course these lines, this will be straight lines, so they pass through infinity. So there will be radial lines like this. There will be radial lines like this. There will be radial lines like this. These are the images of the Steiner circles of the first kind, obtained as a result of transformation S. Now, we may need to consider, we will need in the future, lines that are orthogonal to these lines. And we know from the previous theorems from chapter 5 that these will be circles in which points P and Q are mutually symmetric. So there will be a circle like this. It must be orthogonal. So this angle must be 90 degrees. This angle must be 90 degrees. This angle must be 90 degrees. Yeah. And other circles. And there will be, of course, a circle, a line, which goes right in the middle between P and Q, and it is orthogonal to all these lines, orthogonal to all these circles, right? And there will be a line like this, and so on, a line like this. I ask you to note that points P and Q are not the centers of these lines, but they are symmetric in these lines, yes? And when we form a Möbius transformation, if these lines are orthogonal, these new circles, which are called Steiner circles of the second kind, or Apollonius circles, and maybe this is faster to call them this way, will be orthogonal to these lines, to images of these lines, which are these lines. So these will be circles, of course, centered at the origin. Yes, because if circles are centered at the origin, they will be orthogonal. And suppose this line has as the image this circle, I will make it this line more prominent. Yes, this is the line right in the middle. So these other circles are surrounding Q, so they will surround infinity. It will look like they surround the origin as well, but essentially these are circles around the infinity. And you remember, I think I did talk about this, how to obtain these lines and radial lines from the Riemann sphere by cutting Riemann sphere by the radial lines are obtained by cutting Riemann sphere by vertical planes like this. And like this. And maybe more, let's say like this. Picture is not perfect, but you can imagine these cuts made by the plane. And of course, when we perform the stereographic projection onto the complex plane, yes, these lines will have as images the stereographic projections of this of the points lying on these lines will be the straight lines. Let's say this one. Straight line, and so on. I drawn the two lines, it's messy already without this. Yes? And when we want to obtain these circles, the images of the circles of the second kind, they can be obtained by cutting this globe, by horizontal planes, yes? So this will go like this, and when you take stereographic projection onto the complex plane, yes? If the circle is pretty close to the North Pole, of course it will be a circle of a huge radius, yes? Like this. And when you take a bigger circle like this, it will be, this projection will be closer to the the origin will be a circle of a smaller radius, and eventually this circle will be this one, the unit circle. It kind of divides the plane between circles that are around infinity and that are around the... Of course, this circle must go more prominently. I can erase otherwise from my again. The picture must be good, so this must be more like this. This and so on and so on. And of course, when you cut the lower hemisphere by horizontal planes, you will obtain circles like this. And when you take the projections, the stereographic projections of circles like this, you will get their traces surrounding the origin. Inside it will be circles like this. This is a smaller one, this is a smaller one around the origin. So this will be the origin. Yes? The origin will be the stereographic image of the south pole, and infinity is the stereographic image of the north pole. And when I will write again this formula, W minus P over W minus Q. W is our Tz equals lambda Z minus P over Z minus Q. And lambda, of course, is associated with the motion. Yes? W equals lambda Z in this plane. This is the plane Z W plane. It's actually the same plane, yes, but when we perform the motion, we will obtain W plane. After we subject Z plane, Z capital plane to motion, we obtain W plane. So what kind of motion this will be? The motion of transformation type depends on lambda. The motion depends on lambda. How does it depend on lambda? I think I can erase these illustrations to have some room for writing. This. There are three cases. Lambda may be e to the power I theta, then it is a rotation in ZW plane, right? Because this transformation is rotation. What happens in this case? We rotate these lines of the first kind, we rotate them through some angle theta. Suppose this is angle theta, depending on what is lambda. This is angle theta, yes? This is angle theta. This is angle theta. This is rotation. Yes? This is rotation. So we can illustrate rotations like this. That's one case. Such a transformation, T is called elliptic. Then, the other case, lambda is real and positive. Is from R plus. Then it's a homotety, the transformation is a homotety in ZW plane. Yeah? And of course, elliptic transformation, I did not finish illustration. I will take the red pencil and try to illustrate elliptic transformation. Yeah? This will be. Oh, okay, I will make it black, and then the next one I will make red. So we rotate from one radial line to another. So from one of these circles to another. So it will look approximately like this. Suppose this is angle theta. Rotate through angle theta. It's rotated from this circle, from this circle to this one. So it will go like this. Yeah? Angle theta. It goes around here, so it will go from this circle to this one. It will go like this. Rotations through angle theta. And you can show another parts of the diagram. From this circle to this one, it will go like this. So, these are rotations. You can draw more circles, and then there will be more. This one, and so on. This one. From this circle. So that's what it will be. Now, when lambda is a positive real number, the transformation is a homotety. So what the homotety does, it spreads the plane or shrinks the plane, depending on whether lambda is more than 1 or less than 1, from the origin or towards the origin. Suppose it is moving it outward, suppose it goes like this. This and so on, right? So what happens? You go along the circles that are straight lines from one of these orthogonal circles to another. So it will go, it will look like this, for instance, from one orthogonal circle to another. Suppose it will go like this. Here, when we move away from the origin, we move closer to the infinity, yes? So here we are away from the origin, so we must move closer to the infinity, so the motion will go like this, closer to point Q, like this, yeah? It looks counterintuitive because it looks like we make our radii bigger, but when we move our radii bigger, we are approaching point Q, which is pre-image of infinity, right? So it goes like this, and so on. And from P we go like this. Maybe there is another circle, something here, and then we will go like this. I did not show all the circles, right? And so on and so on. So we will make calculation to see how it works and to see exactly what these motions are. And there is also another option when lambda is modulus lambda e to the power I theta, where modulus lambda is not 1. So it combines a homothety and rotation, and in this case the transformation T is loxodromic. And loxodromic transformation is really tricky to show, because it goes simultaneously, both extending, shredding, spreading from the origin, and rotating. So it must go along. It starts along the line, but then it also rotates. So it goes goes, and approaches infinity, like this. And nearby will go like this. And so on and so on. And it is not easy to see, but if we take the and here it's even more difficult to see. Here it's even more difficult to see. You can try to show it. It must go like this. It starts along a line, and then it also rotates and rotates and rotates and rotates, and and then it goes like this, and then it goes like this, and it approaches infinity, something like this, like a double spiral. Yes. It goes from point, maybe this picture is getting too messy. I will show you in a second how it looks on the Riemann sphere, and it actually allows you to understand what's going on. If you have point P here and point Q here, and you have these lines that connect P and Q, and the lines that are connect P and Q like this. A few of them. Bigger radius, and it looks like this. Yeah. And like this. And then the orthogonal circles. Yeah, orthogonal circles. This. This. Like this. This. And what will be Loxodromic transformation? It wants to go along this first type of circles that becomes lines, but eventually it also rotates, so it goes like this. And, in my picture it looks like it's coming to the points P and Q, but actually it is approaching them infinitely long. That's what Loxodromic transformation. It looks like this. If this is P and this is Q, it starts like this, and so on. And the convenient way actually to see how it works is to take a model of the Riemann sphere. This is the Riemann sphere. I have prepared it a little bit. I made a little cut here, and then I want to go from the North Pole. Actually, I have to go from the South Pole. Suppose this is South Pole, because I go from 0 and then to infinity. Yes? But it doesn't matter. It's convenient for me to hold this upwards. So we will go while we are cutting through, and we also rotate around the sphere. It doesn't go very easily. This particular orange. Goes better. So you can see what's going on. Yeah, we are going from the north, from the south pole actually, and we go around, but we increase the radius, and we also move along the sphere And now we are approaching the North Pole. Of course I rotated it for convenience, because I have to hold it somehow. It's not easy anyway. So you see, it goes like this, like this, like this. And eventually you will arrive here at the North Pole. And if you remove all of this peel, and you can, I think I have to make a better model with a softer, to take an orange with softer skin, because this one is really very hard. And then you would see that what you have removed from the orange can be flattened down on a surface, and you will get a figure It looks like this. So if you peel it properly, if you peel the orange properly, it has softer skin. It will look like this. And indeed, if you, here we don't have, but we do, so try to make this model with mandarin, which is peeled easily, then you can do it by hands, and you can go very carefully with this orange. My model, you got the idea, but the model itself did not work very well, because the peel is too hard and it breaks also. Now, these are the three types of Möbius transformations with two fixed points. And now we would like to study these types. I don't think we will do any calculations with Loxodromic and any graphs of Loxodromic transformation, because it's getting too difficult. We just know that they exist, but we will consider some other examples. So our idea is the following. We are given a transformation, we have to find the fixed points, find the, if it has two fixed points, we will consider examples today with two fixed points. Classify this transformation by determining the value of lambda, and then try to sketch the picture. And we will have an assignment in which you are required to sketch at least two realistic moves of Steiner circles. First kind or second kind, depending on what kind of transformation you have. For two fixed points, you will always have elliptic or hyperbolic in your assignments. We will not have Loxodromic. If you get Loxodromic, we classify it as it's a Loxodromic transformation. You must know it's happened, but in order to make pictures, we will do them for two cases. So in your textbook, it's problem number 3, and I will consider problem 3D. A and C are in your assignment, and you will see the solutions. I solved them in detail. You will see the solutions written, and I will consider problem 3D, and I will consider one more at least problem. So we would have one example of an elliptic transformation, one example of a hyperbolic transformation, at least one. They do take time to consider. So what's in this problem? Tz equals negative z divided of 1 plus 1 plus I z minus I. This is formula 1 for our transformation. You can see it's a Möbius transformation. So what do we need to do? First of all, fixed points. So fixed points, that's how we do it. Second, write a normal form. Third, find lambda, classify t. Fourth, we will try to sketch the motion of Steiner's circles, and at least one or two must be for real. I say to say, must be precise. Precise to make some precise pictures. That's our program with which we will proceed. So first of all, fixed points. Z equals T of Z. Yes, point Z is immovable by transformation. We know that every Möbius transformation will have one or two fixed points. So let's calculate for this case. Z equals negative Z divided by 1 plus I Z minus I. Let's multiply by the denominator. So we will have 1 plus I Z squared minus I Z equals negative Z, or 1 plus I Z squared minus Z multiplied, we bring it here, it will be 1 minus I, right? When we bring Z, plus plus Z minus I Z plus Z equals to 0. Factor out Z, we will have 1 plus I Z plus 1 minus I equals to 0. So 1 root is Z1 is equal to 0. That's what we can say out P, for instance. And which will P, which will be Q, we will decide. And then the other one we find from 1 plus I. Yes, this bracket may be also 0. Z plus 1 minus I is equal to 0. So Z equals, I bring it to the right hand side, negative 1 plus I divided by 1 plus I. And in order to divide, I will multiply and divide by the conjugate to the denominator. 1 minus I, 1 minus I. So it will be negative 1 plus I and I minus I plus 1 divided by 1 squared plus 1 squared. Modulus squared of 1 plus I. So it will be 1 minus 1 cancel each other, 2I divided by 2, it will be I. Z2 is equal to I, and this will be presumably our point Q. And this will be presumably our point Q. And so we have fixed points. So let's say fixed points z equals to 0, z equals to I. So how to write the normal form? Normal form is what? W minus P over W minus Q equals lambda Z minus P over Z minus Q. Right? So in our case it will be W minus 0 over W minus I equals lambda Z minus 0 over Z minus I. Or W over W minus I equals lambda Z over Z minus I. This is the normal form of this transformation. I will call it formula star, for instance, or I will assign it some number later on. But then the next thing you have to determine the value of lambda. So we'll do it in the next lecture.